There are a few things that you want to understand about regression before we go on. One, note that sometimes in any regression, and some of you will be facing this, in some regressions, especially in panel data, you may have to take the logarithm of some of the independent variables. Why do you do that? Because you want to impose a constant percentage effect. Sometimes you believe that inflation is affecting the behavior of that variable. For example, when you take something like wage, if you are looking at the regression of wage on those independent variables, wage is, the data you are going to get is not the real data. The data you are going to get is the nominal data. And we know that the nominal wage is affected by inflation. Okay, so you got to deflate the wage or the price so that you can have it in real wage, so that can take care of inflation. And one way of doing that is by taking the logarithm of the log linear function of the variable. So sometimes you see that in some regressions, people will take the log. It is to impose that constant percentage change. Okay. Sometimes some people too will take a square. I just showed you an example. Okay, you take a square of some of the independent variables. The reason is because you believe that the relationship between the two independent variables is not linear. It is non-linear. I gave you an example. Take something like the size of a company. It has been realized that the size of the company can rise as the company is in operation. The size rise and rise and rise, and over time, the size is likely to fall, especially in mega mergers. Okay? When the company is merging and merging and merging over time, it becomes too big. And when you become too big, you can't monitor people. Okay? The CEO and an employee will be in the lift, and the employee never knew that that is the CEO, and the CEO never know that that is even the employee, because there's so much, there's so many people going on. Okay, so many things going on, and nobody can monitor. There's bad monitoring. And sometimes to some people too will become so many that nobody will work. For example, if you look at some government parastatals, you will see that in the morning, the person will start reading the newspaper, will start watching cantata, will start chewing granite and other things. Over time, work is not done. By 12 o'clock, 1 o'clock, the person is going for lunch, and work hasn't been done. Because so many people are there, nobody is doing it. Everybody is checking. Such a situation, things will rise, get to a point, and they will fall. And if there is a theory underlining these things, and you got to have some theoretical perspectives on this before you include such squares. And also, sometimes you have to interact some variables. For example, in the context what I just showed you about multicollinearity, if you believe strongly that education and experience are highly multicollinear, okay, and it's so high, you may decide to drop one of them, because one will be just redundant in the model. So removing that one will not spoil anything. For example, I told you about the woman who came to lie about the husband. Even if it was true, there was no need for the woman to come to the law court to testify, because the jury would have understood that, oh, come on, this woman is not going to lie against the husband. So she coming is just waste of time, a repetition, okay, redundancy, a waste of time of the court, because she's just going to repeat the same thing. So removing her from the court model will not spoil anything, will not lose any information, because the husband will give us that information anyway. And that is why sometimes so in such a case, what you do is that you will remove one, but after removing that one, you will now create a new variable where you have multiplied that one together. So in this case, you multiply the experience by the education and create another variable, and that is called the interaction variable. And then now look at whether their interaction is powerful enough. Okay, yes, you are removing one doesn't mean that the other one must go fully, but you must interact that one. So in this case, it's not the same variable. That interaction might show something. And there's a difference between interaction and mediation. Okay, in such structural equations, sometimes you might do something related to mediation. Okay, but mediation is where you have three variables. X is affecting M, and M affects Y. That's mediation. But interaction is where both X and M are both affecting Y. Okay. where the effect of x on y depends on a third variable m, okay, which is what I just explained about interaction. So please note the difference between mediation and interaction. Sometimes they can be confusing. Okay, now at this stage, how do we find the beta parameter? Let me just take you back to where we were. Look at this information that we had. Okay, we had a wage equation and we had a wage model. And we saw that the wage equation, the beta parameters have been found. What is the process to find the estimator, that beta parameter? How do we get the numerical value of the beta? There are several ways, several methods of arriving at the beta parameter. The approach is known as estimator. The estimator is like a rule or recipe where the data is transformed into an estimate. And you can see that that beta value, we now got a numerical value for it. So in order to get the actual value of the beta parameter, we need to use one of these estimators. The first estimator is known as Ols Estimator. Many of you have heard about it. OLS means Ordinary Least Squares by Adrien Marie Legendre in 1805. The next one is known as the Maximum Likelihood Estimation. It is another estimator. The next one is known as the GLS, Generalized Least Square Estimator by Atkin in 1935. Then we have the Feasible Generalized Least Squares, okay, which is a practical form of the weighted least square. Guess what? Are we going to be able to do all of these? Well, to be honest, you don't need to even spend more than an hour to do all of this. You can do them easily in R. And we shall run these models in R. But we will understand how they are working first before. I'm not going to be able to explain to you all of them, how they work. I'm rather going to end with a beautifully complex mathematical derivation of how we get the beta. Do you remember this equation? The goal of any regression is to find the OLS estimates, the betas, which eventually becomes numbers. We are going to use matrix here to be able to find our answers. I'm going to create a beautiful new slide here. Moderation is the same as mediation. It's the same as mediation, so please note. I'm going to create a new page here and then derive this thing for you. Please watch me, because this might not be that simple for a lot of people. So sometimes it's important that you follow me. All right. So now we have our regression, and this is our regression. Our regression is given by y equals to x beta plus the error term. Okay. And the error term, as I indicated, I'll be using things like ui or epsilon I. Now, as it stands now, you know that the y is an independent variable, the x is the several independent variables, the beta are the several beta parameters. This epsilon is the error term. We are trying to fish out the beta. Well, fishing out the beta is not simple because you have to have an understanding of some assumptions. So what I'm going to do first of all is I'm going to multiply everything. Remember, x is a matrix. I'm going to multiply everything by x prime. Everything by x prime. Just watch me. So I'll multiply x prime by the y, multiply x prime by the x beta, and then multiply x prime by the epsilon. I have not done anything wrong with the model. I have not changed the model. Everything is intact. There's no problem with that. So far, so good. Now, at this stage, it's very important to appreciate some few things. Okay. Once again, what I'm going to do is that, and it's very important you appreciate some of these things, because if sometimes if a person doesn't appreciate some of the things that they see, it can hurt. So it's important to appreciate that. So I want to believe that you appreciate what we are doing here. The next thing we are going to do is to multiply through by x prime, multiply through by x prime x to the power -1. First of all, let me tell you something about x prime. Now, you know that x prime, as we know all these while, if you have done a little bit of matrix, okay, this x prime looks more at the inverse of x. Okay, and then the x prime to the power -1 is a transpose of x. Okay. So we are using those principles to be able to arrive. So I'm going to multiply through by that. So that means on the left here, I will have x prime x to the power -1, and then what is already there, x prime y. And then, oops, and then equal to the same x prime x to the power -1, and then x prime x beta plus x prime x to the power -1, and then x prime epsilon. Okay. Now, what I'm going to do is that I'm going to take the expectation of this. And one of the things you should notice is that when you take expectation of anything that is already in the matrix, x is in the matrix, y is in the matrix, when you take expectation of it, you get the same thing. Okay. So please note, when you take expectation, you get the same thing. There are three parts. Okay, let me just circle them for you to see. There are three parts to this. The first part is this one here. The second part is that one there. And the third part is this one here. Now, the third part is very important because there is an epsilon there. And you remember that we indicated that the expected value of the error term, and I'm about to take the expected value here. And just remind yourself about one of the assumptions of regression. If only you can remember the name. It's called the zero mean value. Do you remember? Which says that the expected value of the error term given the x should be 0. Do you remember that? The expected value. That way the expected value simply means mean. Those of you in finance will understand. Okay. So the expected value of the error term given x is 0. So if I should take the expected value of this, we are going to have 0. So this bottom one here is going to be 0. And I told you that whenever you take expected value here of any matrices, you get the same thing. Now watch this second one. If you look at this, do you remember the rules of index and exponents? Exponents and index. So if you have x -1 plus x2 or times x2, okay, you can take 1x and then you have -1 plus 2. So that becomes x1 to the power 1, which is x. Okay, so that's the same principle. This one is to the power -1, and 1 is also to the power +1, but we don't write a +1. Okay, so the two of them will cancel. Okay, in principle, because one would take, so you have -1 and +1, which will be what? 0. Okay, and any number raised to the power 0 is 1. So the whole thing is more or less gone. So we are left with the expected value of beta. So here we'll be left with the expected value of beta. And then on the left-hand side today, you have this. Now, one of the assumptions on the left-hand side will have the same thing, which is x prime x to the power -1 x prime y. So we are concluding that what is the expected value of beta? Well, when you learn one of the assumptions of regression, there's something we call unbiasedness. Okay, the beta cap is an unbiased version of the true beta. Okay, so the beta cap is expected value of beta. So the expected value of beta will be something we call beta cap, which is the Ols estimator. And this will be equal to the left-hand side here, which is x prime x, okay, to the power -1 x prime y. This statement that you are seeing there, that thing is the actual value of the beta cap. Now, why a cap? A cap is there to simply indicate that it's been estimated. So that is the estimated value of the beta. That is the 0.85 that you saw, the number that you saw. That number that you saw is an actual number which was derived. All of them were derived. Okay? Those numbers that you saw, all of them were derived from this matrix. Now, so it means that if you know any table, any data frame, and you put it into this matrix, it will give you all the beta parameters easily. Okay. And I'm going to show you conclusively how this is achieved by that. So the beta cap, OLS, is the x prime x to the power -1 x prime y. And the way you derive this thing generally, this is a easy way of deriving it, but I didn't show the easy way. Check the Woodridge book, Econometrics, 2013 Woodridge. Okay, he would have shown you how this is done. I'm just letting you know that you got to understand a bit of the theoretical underpinnings of this. Okay, you got to some way, somehow get this thing. One day you will use it to prove that you did it. Okay, the next time what we are going to do is to be able to understand the variance. So this means that every time you are finding the mean, and please, I want to go back to this section here. The goal is to find the beta. I remember I told you that. Now, to find the beta, you don't just find the beta, but you must know the mean of the beta. What is the mean